Hi again, Calc AB students. Thanks again for checking out the videos last week from Ms. Hoagie. Those were impressive, right? Yeah, her handwriting is so neat. And her explanations were awesome for you guys. So the part of the fun with Calc AB this year is we're going to trade off making these videos. So if you like Ms. Hoagie's videos, don't worry, she will be back. But you're going to have to put up with me for a video or two now. Now that we've understand some things about limits and some of the properties of limits and how we find limits, we're going to look at one of the really big ideas for us in this first chapter with how we use limits. And this idea is actually an idea you probably have seen before. So we're going to talk about how do we know if a function is continuous or what makes a function continuous. And when you were in your calc or pre-calculus classes, you probably got some kind of definition from your teacher that was like, hey, you can tell if a function is continuous just by how you draw its graph. And your teacher probably said something like, hey, the graph of f of x is a continuous function if you can draw the graph without lifting your pencil off the paper. And that's actually a really good definition. I don't hate that at all. I think that's a great way to think about continuity because you're continuously drawing that line, and that makes the function continuous. But of course, in calculus, we want to get a little more technical. We want to get more in depth on that, and not take such a pre-calculus kind of view of it. So we're going to get in there and we're going to define continuity a little bit differently. And so in calculus, it starts with different kinds of continuity. We're going to start off with continuity at a single point. So continuity at a point. And then we're going to move to continuity on an open interval, and we'll talk about what we mean by open interval. And then we're going to talk about continuity on a closed interval. Hopefully we can get all that done without running too much over our goal time frame. So continuity at a point. So what we would say is that a function, and we'll name our function f. Oh, I hit a button there, I didn't mean to. Our function f is continuous at a point, we're going to call it C, if the following conditions are met. All right. So definition of continuity starts off with what do we define this function, and we say, hey, we will say this function is continuous at a single point, and then we'll take a look at how do we get further into it, like continuous on an interval. So the conditions are condition number one, f of c is defined. Okay. Yeah, so obviously when you're drawing the curve, the function had a y coordinate for every x value. So f of c had to be defined. Two, the limit as x approaches c of f of x has to exist. Okay, yeah, you have to have a limit that exists. So last time with Ms. Hoagie, you learned that there were three cases where a limit fails to exist, right? Unbounded, function is unbounded. The function oscillates with increasing frequency, so you can't find the limit there. Or maybe the left and the right sides approach different values. So that's how we know a function doesn't have a limit. So not one of those three cases. The limit exists. And the third condition for continuity ties these two ideas together, that the limit as x approaches c of f of x has to equal f of c. So the function is approaching a value, and I think, well, in my class anyway, I know I made a pretty big deal of we don't care what happens at c for the limit. Okay, well, but for continuity, we definitely care about what happens at c. You have to have the function approaching the value f of c when you're talking about continuity. So if I were to maybe draw some graphs for you, we could kind of look at like maybe why some of these functions are not continuous. And I think you'll see that if we go back to that pre-calc definition, I can't draw any of these without lifting my pencil off the paper. So it's pretty clear that again, that working definition is still a good one to when we're just looking to see if a function is continuous or not. Now in calculus, we want to say why it's not. So which of these three conditions did we violate? So my first graph here, let's take a look. I'm going to draw it out for you. And you'll see that, well, we'll see if you can figure out why this function is not continuous at our point C. And so the function I'm going to draw goes like this. Like so. And right here, underneath here, that's C. And so why does this function f of x, why would we say it is not continuous at point C? Because that's an open circle. So f of C is undefined. Right there, f of C is undefined. So as we saw previously, that means the function is not continuous. Cool. What about this one? Let's take a look. Oh, I don't want that color. I want this color. And this time, I'm going to draw my function again. And this time, my function goes like this. And right here, oh boy, that's not very straight, is it? Sorry, guys. That's C. That's supposed to be curving down like it's an asymptote there, guys. So a little tough to do sometimes on the old drawing pad here, even with the handy dandy stylus. There we go. So there's f of x. And why does this function lack continuity at C? Well, you might be thinking, hey, it's the same as the first graph, right? F of C is undefined, and you'd be right. It also violates the second condition, right? What's the limit as x approaches C? It's unbounded. So this one actually violates two of the conditions right off the bat. And I suppose technically it violates all three. So yeah, so we have a function where the limit doesn't exist. We have a function where it's undefined at C. Lots of things going wrong with that function. My third graph. Why do I always forget to change the color? All right. We're going to draw this one so that it does this. And, oh, that erased the whole thing. What? I guess I gotta do it like this, guys. Sorry. This is C here. And here's f of C right here. So does the limit exist? Of course, the limit does exist. Left and right hand limits both approaching this point right here. That's the limit as x approaches C of f of x. Is the function defined at C? Sure. Here's f of C right down here. So what's the problem? Well, the problem is, of course, that the limit does not equal f of C. F of C is down here. The limit's up here. Yeah, we have a violation of the third one of our criteria for continuous at the point C. So yeah, so I think understanding it graphically, of course, in GNA is important. And understanding it in words, which was our definition previously on the previous page here, you know, that's part of the GNA acronym. And I wanted you to see what those look like. Now, at this point, we want to switch over and talk about, well, okay, so now we know what it means to be continuous at a point. What does it mean to be continuous on an interval? And for us, we're going to define first a an open interval and a closed interval. And let me just first of all say that an open interval, a set of numbers on a number line that does not include the endpoints. Okay, so for our open interval, we are not talking about what happens at the endpoints of the interval. Okay, so if you had a number line, like old school number line like this, okay, and you were looking at what happens between, I don't know, let's say the point here is and the point up here, okay. I shouldn't do that with those, should I? It should be open dots, right, from your old algebra days, right? That does not include the intervals. Okay, so maybe this one down here, maybe this is like -2 and maybe this is +4. So that would be the open interval from -2 to 4. It does not include the endpoints. If we wrote it as an inequality, we would write it like this. Okay, and for us, we're going to use interval notation a lot of times. When we use a round bracket, like a parenthesis on the end, that means it does not include the endpoints. Okay, that's what we mean by open interval. Okay, so conversely, can you imagine what closed interval must mean? Yeah, exactly. Closed interval, oops. Well, that includes the endpoints. Okay. If I use my same kind of interval up there, it's above there, right? All I would do to include the endpoints, I would have this notation if it was an inequality. Okay. The number line, I would shade in my endpoints, the dots, right? Okay. And for us in calculus, what we're going to use a lot of the time is squared off brackets. So -2 to 4 would be the closed interval that includes -2 and 4. Okay, so that may be review for some of you, but sometimes I've seen in first years especially that those are kind of new ideas. And so I want to make sure that we have that notation so that when I'm saying how we define continuity on an open interval versus closed interval, you understand the difference. So, okay, so what happens for us when we start talking about continuity on an interval is really, I think the open interval is pretty easy. So continuity, on the open interval is pretty easy to define, because all we say is that for a function is continuous on the open interval, let me say a function is continuous on the open interval a to b if it is continuous for all c in the interval a to b. Yeah, super easy. Yeah, as long as the function is continuous for every c in between a and b, not including the endpoints, then yeah, the function is continuous on the open interval. Okay. So the easy peasy one. Okay. Now the more challenging one is continuity on. Whoa, just changed colors on us there. There we go. The more challenging one for us is closed interval, and I think we'll see why in just a second. Continuity on a closed interval. Okay. A function is continuous, on the closed interval a to b. Well, I can't just say if it's continuous for all the points in the interval a to b, including the endpoints. Okay, and why can't we do that? Well, because remember, back when Ms. Hoagie was teaching you about functions and when their limits didn't exist, one of the definitions was when the limit from the left and the limit from the right don't agree. Okay, well, think about that for a second. At a, okay, the left endpoint of the interval, how can we approach that from both sides and get the same value? We're basically saying, hey, the universe stops at a. There's nothing smaller than a for this function right now. There's no way to prove the limit from the left of a is the same as the limit from the right of a. Okay. Similar problems happens at b. There's no way to prove the limit at b exists, let alone that it's f of b, right? It has to be f of b. We'll get to all that in a minute. Same with f of a on the other side. But you can't prove the limit exists because there's nowhere to the right of it. There's nothing that exists that is bigger than b as far as we're concerned when we restrict our interval. And so we really need to learn about one-sided limit notation, and that's where what happens in continuity on a closed interval. So what we say is the function is continuous on the closed interval a to b if the function is continuous on the open interval a to b, and then here's where we get some new notation. Because I only can approach a from one side, okay, I'm going to draw a picture so we can get a better feel for it. So let me draw my standard graph here. Okay, and here's a. Oh my goodness. I have the hardest time drawing straight up and down on this thing. A, and here's, oh my gosh, here's B over here. The universe stops here, so I'm gonna redraw the function apparently, so that it doesn't go past those points. Here's f of a, here's f of b, and so what we're going to do is we're going to say, hey, look, we can only approach a from this side. We can only approach b from this side. But that's enough. We will be okay here. What we say is the limit, the function is continuous on the closed interval a to b if it's continuous on the open interval a to b, and the limit as x approaches a from the right, and I'm going to put a little plus sign as a superscript on a, of f of x equals f of a. Okay, so you see that little plus sign means only worry about the one-sided limit. So that's a one-sided limit notation. And the limit as x approaches b from the left side equals f of b. So there you go, the definition of continuity on a closed interval, and it involves some new notation. Okay, it involves notation where we have a one-sided limit, and that's how we do that. X approaches a from the right when you see the plus sign. X approaches b from the left when you see the negative sign. And that's what we mean by one-sided limits. And the limit before, when we said, hey, left and right-hand limits don't agree, now you have some notation to kind of describe that. And those one-sided limits are a big part of continuity on a closed interval. All right. No, it's so weird because there's nobody to ask if you have any questions. Normally, I would ask if you had any questions at this point. But those are the definitions of continuity at a point, open and closed interval. And I will show you one application of continuity But I can tell you that most of the theorems that we're going to work with for the rest of the year, they start with some language that usually says, let f be a function that is continuous on an interval. Okay. And a lot of people tend to read that and just kind of go, okay, of course, and just forget about it. But that's really important, because what we're saying is, like, if the function is not continuous on the interval where we're describing, then we run into a really big problem. And the function lacking continuity could invalidate the entire theorem. So we got to make sure that we have continuity on that interval. All right, so now we have our definition of continuity figured out. What do we do with it? Well, usually when we're answering questions about continuity, when we're working with functions, that we get the question about, is this function continuous? And that's where we'll be using our definition of continuity. Honestly, though, most of the time in the continuity discussion, like they'll say, like, discuss the continuity of a function. What they're really looking for is, where's the function not continuous? And there are two types of discontinuities that we're going to deal with. There are removable discontinuities. Oops. Removable discontinuities. And these are discontinuities that can be removed to create continuous functions. Okay, and we'll take a look at those in a second. And then we have the other kind, which you've probably already guessed. Yeah, non-removable discontinuities. They can't. Yeah, basically, you can't get rid of them. Okay, now, typically when we start talking about removable discontinuities, these are holes in the graph. Okay, so usually those are holes in the graph. And when we're talking about non-removable, these are asymptotes. All right, so typically speaking, and I'm saying, generalizing here, but this is usually the way it works. Yeah, we have a removable discontinuity is one where, oh, you just take it out and then now you have a nice continuous function, and that's usually a hole in the graph. Okay, and then we have the non-removable discontinuity, and those can't be removed through any kind of algebra, and those typically make some kind of a asymptote in your graph. So if we come over to Desmos here, we'll take a look at a few different examples of those discontinuities we were just talking about. So this is an example, I think, very similar to one Ms. Hoagie showed you on her video earlier. And it's, I'm graphing, as you can see highlighted in red here, the line x squared minus 1 over x plus 1. Now, why is that a line? That looks like it should be some kind of rational function. And as you know, this is because there is a discontinuity here at x equals 1. So in our graph, sorry, at x equals -1 is what I meant. You could see, there we go, it highlights, and it is an open circle, and you can see that that is undefined. But if you look at the graph, it doesn't appear to have a discontinuity to it. We only know that because we can go and hover over exactly x equals -1. So what we could do with some algebra, and I showed you this earlier, is remove that discontinuity. Now I'm going to lay the blue graph for just x minus 1, and notice it's exactly the same line, except at that point when x is equal to -1. Now you can see at x equals -1, we have a -2 value. And so that just means that we have removed that discontinuity, and that is a removable discontinuity. If I look at this function here, this is the square root of x plus 1 minus 1 over x. And right here at x equals 0, we do have a discontinuity. Oops, trying to use my stylus to point there, and that's a little tough. So, oh, come on, just hold still. There we are. You can see the hole. Okay, using a rationalization technique that Mrs. Hoagie showed you already, I can remove that discontinuity. I'm going to put this purple function down and remove the green function, and look, it's identical. Put the green function back and remove it. And the only difference is now at x equals 0, there's no more discontinuity. It's 0.5. So those are removable discontinuities. The graphs look exactly the same everywhere except at that one point where the discontinuity was. Through the miracle that is algebra, we removed that discontinuity. This graph, this black graph here, you can see it has a non-removable discontinuity. Okay, there is a vertical asymptote on this graph. If I were back in our algebra 2 days, right, we would say, oh, look, over here at x equals -1, there's a vertical line that the graph gets infinitely close to. Oops, I moved that bottom over, and now it's crossing it, but it's not vertical. And you can see that that discontinuity there's nothing I can do to remove that. There's no hole. There's an actual vertical asymptote there. But if you look over here at the function, you'll see that there's another discontinuity at x equals +2. If x were +2, we would have a discontinuity. But in our graph over here at x equals +2, oh, come on. I can't do it with the stylus, guys, sorry. You see we do have an undefined point. So there's a hole in our graph, okay? And I know it's going to be a hole because when I do a little bit of factorization on our numerator, right, I get that x plus 2, x minus 2 over x plus 1, x minus 2, those cancel out. And so that's a removable discontinuity. And you can tell because it's just a hole in the graph right there. Okay, the non-removable remains as a vertical asymptote. And let me clear those annotations out of there. And sure enough, if I turn on the red function here, well, the black one's on top of it, you can see they match exactly. The big difference is at x equals +2, the red function will exist. So that is the difference between a removable and a non-removable discontinuity. They're pretty easy to spot, the non-removables, because it's just like what we are used to looking for from algebra 2. Now what we're talking about are these removable ones, the discontinuities that can come out of there. And if you notice, in terms of the limits, the non-removable one, what's the limit as x approaches -1? It's undefined, right? It's positive infinity if we approach from the right. It's negative infinity if we approach from the left. That's unbounded behavior. So that limit does not exist. But when we approach the removable discontinuity at x equals 2, we definitely have a function value there as we get closer and closer to 2. So just a good thing to remember that the non-removable ones also, usually the limit will exist there. So that is it for today. We've talked a lot about continuity. We've talked a lot about discontinuity. We've talked a lot about limits. And this is our first big application of those ideas. So thank you guys so much. And I will talk to you soon. Have a good day.